morning, guys. So today we will start our next topic, that is one-dimensional heat conduction with convection actually. Okay. So in previous lecture, in previous 2 to 3 lectures, we have covered first derivation part of one-dimensional steady-state heat conduction. Okay, in which we have derived the elemental conductive stiffness matrix for this one-dimensional steady-state heat transfer problems. Okay. Now in this lecture we will see how to determine the elemental stiffness matrix for one-dimensional steady-state heat conduction with convection as well as. Okay. So if we consider a body in which heat is transferred from this end to this end, it means heat transfer takes place with the conduction mode, as well as this heat transfer is taking place with the convection mode. It means what? It is surrounded. If this circumferential area is not insulated, it means what? The heat transfer will take place with the help of convection. Okay. So as we know that from the heat transfer subject or concept, that if this is not insulated and if any fluid medium is surrounding to this body, then the heat transfer will take place through convection. So as we know that the heat loss through convection is given by H into A delta T. Okay, this is the heat loss due to convection and it is denoted by letter QH. Okay, so as we know that this is QH, it is given in watt. So if we consider it is in a watt per meter square, then it will become H delta T, and where delta T is nothing but your T surface minus T infinity, where Ts is what your the surface temperature of this body and T infinity was what it is what your the fluid medium temperature or ambient temperature. Okay, so in this way heat transfer will take place by this convection mode. Okay, so in this problem by using both modes, means by using conduction as well as convection, it is transferred to the surrounding. Okay, so here this is your conduction mode and the heat transfer through this fluid medium, it is what your convection mode. Okay, so now we will derive the elemental stiffness matrix for this case. Okay, so as we know that we have first derived the elemental conductive stiffness matrix for one-dimensional steady-state conduction only. Now in this case we will derive the elemental conductive as well as convective stiffness matrix. It means what? You will get first conductive stiffness matrix, then you will get convective stiffness matrix, and finally you will get first boundary conditions for conduction as well as boundary condition for convection. Okay, so first, as we have derived first elemental stiffness matrix for conduction, so we know that this is what? Kx into A divided by T 1 minus 1 minus 1 into temperature is equal to QAL by 2 plus area times Qx1 Qx out, Qx in Qx out. So this was your differential. This is your algebraic equation which we have derived from the governing differential equation, in which it is your elemental conductive stiffness matrix. This is your temperature vector. This is your boundary condition due to heat generation, and this is your boundary condition due to heat conduction. Okay, so for one-dimensional steady-state heat conduction, we have derived these equations. Means we have got these elements: first element, second element, third element. Okay, or first parameter, second parameter, third parameter. Now we are adding here the convection effect also. So for this LHS side, we need to add one term, that is we need to add elemental convective stiffness matrix on LHS side. Similarly, we need to add some one or two terms related to your convection boundary condition. So how this equation will be going to see, we will see, or we will derive such equation, or first we will try to derive the elemental convective stiffness matrix. Okay, with the help of our governing differential for this one-dimensional steady-state heat conduction as well as heat convection problems. Okay, so this is the basic. So we know that the governing differential equation for steady-state heat conduction. So as we know that the governing differential equation for steady-state heat conduction is given by formula our equation kx d square p by dx square plus q is equal to 0. This is the governing differential equation for steady state heat conduction. But we need the governing differential equation for steady state one dimensional heat conduction with convection. So this will be changed to kx d square p by dx square plus q is equal to h into p divided by l. This equation it will become h into p divided by a in bracket T minus T in P, where T is the surface temperature of the body, H is the coefficient of convection, P is the perimeter, A is the area. Okay, so in this way, it is one term it is added on the RHS side instead of this equation. Okay, so here only one term is added on RHS side, and this is the equation for one dimensional heat conduction with convection. Okay, so this is the governing differential equation. Now we need to, okay, this is our governing differential equation. Now by using this governing differential equation, we need to derive the elemental convective stiffness matrix as well as conductive stiffness matrix. Okay, so what is the procedure? By using Galerkin's approach, we know that the Galerkin's approach is given by this formula over length x1 to x2, because we have chosen this element where q in and q out, and this is the T infinity, means heat transfer is taking place with this fluid medium by using convection concept. Okay, so this is your first element, first node, second node. We will use same shape functions for this case also. Here the temperature distribution can be written as T1 N1 plus T2 N2, where N1 and N2 these are the shape functions. This is nothing but 1 minus x by L, and N2 is nothing but x by L. We have already used these shape functions during our one dimensional steady state heat conduction. Okay, so same shape functions will be used to derive this equation. So as we know that from Galerkin's approach, we know that differential equation integration over limits x1 to x2 means from 0 to length L. So we can write it as from 0 to length L differential equation into shape function into control volume. So control volume, it is nothing but area into dx, because we have initially it is as well as a dx length and of area A. So volume will be dV will become A times dx. Okay, so this is A times dx, which must be equal to 0. Now instead of this governing differential equation, we will put this equation. So this equation finally will become kx d square q by dx square plus q minus hp upon a in bracket t minus t infinity is equal to 0. So we will put this governing differential equation there. So we will get into shape function. Shape function is what? Ni of x. Okay. So we can write, we will write down this governing differential equation as kx d square p by dx square plus q minus hp upon area in bracket t minus t infinity and this is actually bracket, or you can simply add a curly bracket 0 to L in this bracket into Ni of x area times dx is equal to 0. Now we need to derive this equation to get the convective stiffness matrix as well as convective stiffness matrix. So if we simplify this, so we will get 0 to L. So by multiplying each term to this Ni of x into area into dx. So where area is common actually. So area will become common. Actually this area is common, so it will become 0. When it will shift to the RHS side, so it will become 0. So area is cancelled. So what will become? Kx into d square t by dx square into Ni of x dx plus q times Ni of x dx minus h into p by k times t minus t infinity into Ni of x dx is equal to 0. Okay, so this is the integration that we need to solve. So how to solve this integration? So first, okay, so for this part we need to simplify this integration first. Then again this is a simple step. Then again this is also a simple step. Why? Because look at this. This t, it is a function of x, and n, it is also a function of x. Why t is a function of x? Because t is nothing but t1 n1 plus t2 n. And now where n1 and n2, these are the functions of x. Because n1 is nothing but 1 minus x by n, and 2 is nothing but x by n. Similarly, n I of x, it is also a function of x. So this is a function of x into this is also a function of x. It means this both terms, these are the functions of x, and we need to integrate with respect to dx. So we need to solve this first step first, and remaining terms are easy because there is only one term of x, also there is one term of x. So we can solve these two parameters easily, but we need to solve this first term, that is kx d square t by dx square into Ni of x into dx. So by using by part or by part rule, okay, by part rule of integration we can solve this step. So how to solve this step? So if we consider this function as u and if we consider this function as v, as we have solved this step in previous lecture also. So here how to solve? So integration of by parts can be written as u integration of v dx minus integration of du by dx integration of v dx. Okay, so by using this by part rule we can solve this as, so here kx, it is a common term, okay, actually. So kx it is a common term. Okay, so we have written this there. So this is u and this is v. So by using this rule you can write u, it is nothing but ni. You can write ni of x integration of d square t by dx square. It is nothing but dt by dx. dt by dx. Okay. Over limits 0 to L. Then minus integration of du by dx means dni by dx. dni by dx integration of v dx. So integration of d square t by dx is nothing but dt by dx into dx. Okay. So this is the first term. Okay, so we have simplified this first term. Now the second term plus q times Ni of x dx integration 0 to L minus integration 0 to L h into p by a t minus t infinity and I of x dx is equal to 0. So the negative terms are taken on positive side and positive terms are taken on arrangement. It means what? If we simplify this step as, if we take this negative term as well as this negative term to RHS side, then equation will become as kx into ni of x dt by dx over 0 to L. This minus term is taken on RHS side plus integration 0 to L q times ni of x dx is equal to, on RHS side we can write this integration 0 to L d L I by dx into dt by dx into dx and remaining is plus term plus integration 0 to L h into p by a recording चल रही है h into p by a p minus t infinity into ni of x dx. Okay, so in this way you can write this equation. Okay, so you can write now this part on RHS side and this part on LHS and this part on RHS. So you will get integration 0 to L d ni by dx dt by dx into dx plus integration 0 to L. Here we will write only a part which is a function of x on LHS. So here it is t, it is a function of x. T infinity is a constant. T it is a function of, or we can split this as integration 0 to L h into p by a into t into ni of x dx minus integration 0 to L h into p by a into t infinity into ni of x dx. Okay, so this term it will be taken on LHS side and this term it will be taken on RHS side. So this what will become plus 0 to L h into p divided by a t times here t times ni of x dx is equal to these two terms. Kx ni of x dt by dx over limits 0 to L plus integration 0 to L q ni of x dx, and this actually this is minus sign on this side, so it will become positive on this other side. So it will become plus integration 0 to L h t by a t infinity into ni of x dx. Okay, so in this way you will get this final equation. Now by putting the values of t for node I is equal to 1 and for I is equal to 2, if we put the value of t as t1 and 1 plus t2 and 2, and also if we put L1 is equal to 1 minus x by L and L2 is equal to x by L, and if we take difference derivative as per this integration, and if we solve this integration part as we have solved this integration part in our previous lecture also. So here if we put for I is equal to 1 you will get first equation, if we put I is equal to 2 you will get second equation, And if we put temperature distribution T as T1 and 1 plus T2 and 2 and also the shape functions as 1 minus x by l and x by l, then by solving this integration and derivative part, we will get final stiffness matrix. Okay, so final stiffness matrix, what will be the final stiffness matrix? So this is this term, it is related to your conductive stiffness matrix. This term is related to your convective stiffness matrix. This term is related to your conductive heat conduction boundary. This is related to your heat generation boundary, and this is related to your convection boundary or convection related boundary. So first, this is related to your conduction boundary, heat generation rate boundary, and convection boundary. Okay, so you will get 5 terms in one equation, and by solving this one equation, you will get the solving this one equation for 2 times. For node I is equal to 1 and for node I is equal to 2, you will get 2 equations, and by writing these 2 equations in matrix form, finally you will get from this first term, you will get the conductive stiffness matrix as Kx into, now A is actually we have replaced Kx by L in bracket 1 minus 1 minus 1 1 into T1 T2 plus, if we solve this integration, you will get the matrix convective stiffness matrix as, so convective stiffness matrix is of H into P into L, H into P into L divided by 6 in bracket 2 1 1 2 into T1 T2 is equal to, okay, so this is the convective stiffness matrix, okay, and is equal to, now from this is the boundary condition due to the heat conduction, so you will get Qx in Qx out plus, this is the boundary condition related to your heat generation source, so this will become Q into A into, here area is actually ignored, so QL by 2 and Q L by 2 plus, from this case you will get the boundary condition related to your convection force vector. Actually this is nothing but your boundary condition related to your convection force vector. Okay, so this is the elemental convection force vector, and it is given by H into P into T infinity into L divided by 2. Similarly, HP T infinity into L divided by 2. Okay, so in this way you will get HP T infinity into L, HP T infinity into L on second. So by solving this equation for 2 times, that is for first node and for I is equal to 2, second node, you will get 2 equations, and by writing these 2 equations you will get this matrix relationship, that is, now this is your conductive stiffness, matrix, then this is your convective stiffness matrix, then this is the heat conduction rate vector, this is your heat generation rate vector, and this is your convective force vector. Okay, so these are the 5 terms which are related to your first term is related to your conductive stiffness matrix, second term is related to your convective stiffness matrix. This is the term which is related to your heat conduction rate vector. This is the term which is related to your heat generation rate vector, or finally this is the convective force vector, or you can say this is the heat conduction force vector, heat generation force vector and heat convection force vector. Okay, so in this way you will get total 5 terms in the final equation, and by using this equation now you can solve the problems which are related to your one-dimensional steady-state heat conduction as well as heat convection. Okay, it means the conduction heat transfer is taking place with both modes, that is with conduction as well as with convection. Okay, so where as you know all the terms, that is Kx is nothing but thermal conductivity, L is the length of the element, T1, T2 these are the temperature distribution within the element, H is the thermal coefficient due to convection, P is the perimeter of that element or of that body, L is the length. This Qxn is heat conducted in, heat conducted out. This Q is heat generation rate, that is it is given in watt per meter cube. Okay, and this T infinity is nothing but surrounding temperature or ambient temperature. Okay, so in this way we have derived this two conductive as well as conductive elemental stiffness matrices for the heat transfer problems which include conduction as well as convection. Okay, and from in next lecture we will solve 1 or 2 examples related to your conduction with convection. Okay, so here I am concluding your lecture and we will see in next lecture some examples. Okay, so thank you.